So today's topic is about dynamic programming, and this is chapter number 15 of Design and Analysis textbook by Corman. So in this topic, we are going to discuss how we can implement the solution by using a dynamic programming strategy. So dynamic programming is very much alike divide and conquer method, which is basically reducing the problem into its sub problem, or you can say reducing the problem into its atomic parts, which can be resolved with a certain technique, and the technique can recombine into the solution for the whole original problem. So what shall be the difference between divide and conquer and dynamic programming, if dynamic is very much alike divide and conquer? The very first thing is that divide and conquer mechanism uh, access all the possible paths to identify the solution, and it never keeps track of those branches or the paths which the solution has already processed. So in the dynamic programming, we always keep remember of those directions of the tree, or you can say the graph, which we have already processed. So it optimizes the problem, it optimizes the solution, and gives us the optimal value with the help of its uh, approach, or you can say its computational strategy. So what we need to do, we need to follow the sequence of these four steps. The very first thing, we need to characterize the structure of an optimal solution. What does it mean? It means that we have to define the problem, and we need to optimize the problem so we can create a structure for the optimal solution. We need to have a recursive solution which defines the value of optimal solution. We need to compute the value of optimal solution typically in a bottom-up fashion. So we need to create a tree which can be traversed in a bottom-up fashion to identify the optimal solution. And finally, we need to construct an optimal solution from the computed information. So these are the basic steps in which we need to establish dynamic algorithm. So the first three steps were the basis of the dynamic programming, whereas the fourth step, which is basically an additional activity which keeps the information what we have done in previous three steps. So it will give us an ease to construct an optimal solution. So we don't need to attempt one activity again and again by using the fourth step. So to understand the dynamic programming, the very first example which is available in the book is a rod cutting problem. And what exactly is rod cutting problem? In this problem, we are having a set of different lengths of the rod. You can see over here that length is defined with different sizes. So it's 1 unit length, length of 2, length of 3, and up to the length of 10 units. And every length corresponds to a certain price. That is, for length 1 is 1 unit, and 2 is 5, and for the length 3 is 8. So with different cuts, there are different prices. So what we need to identify that if we are having a specific piece of rod and we need to get maximum price from that particular piece of rod, so we need to sell that rod in different pieces. For example, if we are having a unit size length of rod, for example 1 unit, so I have one option that I can sell that 1 unit as one whole, because I cannot make fractions of that one whole and get the price of 1 unit. But for example, if I am having a length of 10 units, so I can make different combinations, that I can make 10 unit pieces, or I can make 5 pieces of 2 unit length, or I can make 2 pieces of 5 unit length, or even I can make a few of 1 unit and few of 2 units and few of 3 units to make the total of 10, or I can keep 10 as it is. So what I need, in this problem, I need to get maximum price from the given length of the rod. So how we can deal with this problem? Here is the example solved in the book, in which the book is saying that there is a piece of rod of 4 units. So if we sell the complete piece, the price will be 9 units, and we can make different combinations. So we need to identify that which combination give us maximum price. So here we can see that if we make 2 pieces of 2 units, so every piece will give us the price of $5, or you can say rupees. So the total will give us $10 or 10 rupees for the whole 4 unit length. So how we can get to this solution? There is a very small algorithm over here, which is basically a recursive top-down implementation, which gives us the idea of you can say divide and conquer mechanism. So here is a function that gives us a cut rod p comma n. What is p? P is the array of prices or the list of prices, and n is the list of n is the total number of length which is provided for the calculation. So if n is equal to 0, that means I am not getting any size of rod. So if there is no rod, there will be no price, so the return value will be 0. If I am getting some value of n which is not equal to 0, so that means there is some certain size of n, whether it's 1, 2, 3, 4, whatever. So we need to have a variable in order to compute the maximum price. So here the algorithm says q as a maximum value of the price, which is initially least initialized with the help of minus infinity. So there is an iterative function statement for I is equal to 1 to n. For example, I am getting n4 according to the given example. So here's the length 4, so I can use the same for our solution. So if n is 4, so this loop will start from 1 to n. So if I is equal to 1, the next statement will execute will be like max. We need to calculate the max between two different values. The very first argument is q, and the next argument is another recursive function, is a call of the function. So we need to identify the value of pi. So if I is 1, the pi will give me the value of 1 unit price, that is 1, which is going to be added with cut rod function. Aage dobara there is another, the function is again calling itself. So p is as it is same the array of prices, where n is here n is n minus 1. So I have already taken 1 unit piece, so I am sending for the next call with 1 minus n, or you can say n minus I. So here I is technically 1 here, and n is 4, so 4 minus 1 means 3. So I am recalling the function with p comma 3. So the function goes back to the initial position where p comma 3. There is no need of executing the first two statements. Q again minus of the infinity. Then again there is a for function for I 1 to n. So here n is 3, so it must execute from 1 to 3. So the q is asking q initially minus infinity comma p of I. Here I is again 1, so the value of pi is 1 unit, plus cut rod n minus I. Here n is 3 because this is the inner function, so 3 minus 1 will give me 2, and the next time when it comes down, so it will be 2 minus 1 1, and when it comes down again, so it will be 1 minus 1 will be equal to 0. So once it becomes 0, we know that if n is equal to 0, it starts returning values. So I will get the value of 0. So I received the value 0 over here, and when I receive the value of 0 over here, what shall be the value of pi? At that time, what was I? So I was basically 1 at that time, and p of I means 1. 1 plus 0 is equal to 1, and q was minus infinity. So minus infinity versus 1, what will be the maximum value? The maximum value will be 1. So the q receives 1 and returns q, because in the last iteration, last calling function, when we send the value of n is equal to 1, so the loop terminates after one execution, one iteration, so it will not go more and more. So how we can compute this algorithm? We can have a quick look of this tree. So in the beginning n was 4, the next call n was 3, and in the next call n was 2, and the next call n was 1, and it returns the value of 0. When it turns to 0, it gives the value of 1, and so on. So in this algorithm, you can see that it is making up a tree which is basically executing in the top down fashion. This is flat divide and conquer mechanism. It is not dynamic technique. So here there are a few paths which are very much identical. For example, 1 produces 0. It is as same as 1 produces 0 over here, and 1 produces 0, and 1 produces 0. It comes 4 times. So if I am having one value from these nodes, it must be same to this part and this part and the other one. So why do I need to calculate these paths again and again? Similarly, this whole structure 2 1 0 and 0, it is as same as 2 1 0 and 0. So there are few branches of tree which are very much identical, so we don't need to invest our time and energy into recalculating those branches which were previously done. So what we are doing over here, we are trying to develop a dynamic programming for the optimal rod cutting strategy, and for that we have created two different functions. One is for memoized cut rod, which keeps memory of tracking what we have done. So here the arguments are same, p comma n, but we are having another array which is named with r for remembering things, and the size of the array is from 0 till n. We are calling function we are calling for loop from I 0 to n just to initialize the array of r with minus of the infinities, because we want all the values initially minus infinity, and then we terminate the function by calling the memoized cut rod auxiliary function, which takes 3 arguments, p n, which is as same as cut rod pn, and there is r which is recently initialized with minus infinity, and here is the memoized cut rod auxiliary. So what exactly we are doing over here, we need to see that if r with the value of n is greater than equal to 0, so if something is in the r which is more than or equal to 0, so we can say, okay, if the length of the rod is 4 and r of 4 is more than equal to 0, that means we have already calculated the complete price for the length 4, if 4 is our example, for example. So we can return the value of r, and we don't need to recalculate the whole function. And if n is equal to 0, that means there is no rod, so the q must be 0. Q shall be the variable which gives us the maximum of the price, else q should be equal to minus infinity. If we are having n with different numbers other than 0, so we can initialize q with minus infinity, and the same for loop which we have been using in the previous function, it is as same as the previous one that we are getting the maximum of q versus pi plus function calling itself, that is the recursive technique, memoized cut rod, where p comma n minus 1 comma r. So here the r remains same, and whenever we are returning this thing after the completion of the for loop, before returning the whole function, we are modifying the value of our array to that particular index, that is n. So whenever we pass through a certain path, we keep the value of that particular path. So the next time if we are passing through the same path, we don't need to calculate the path value again and again, because we are keeping the value somewhere in the r. So for example, if n is 2 after the multiple recursive iterations, so every time n is getting minus by 1, so if initially n was 4, then the next call will be n minus 1 3, then n minus 3 minus 1 2. So if n is 2 and it was previously calculated, because if initially r of 2 was keeping the value of minus infinity, but if we already passed through the path, then r of 2 definitely contains the value which is not equal to 0. So at that time we don't need to enter into the for loop and calling the function again and again. We just simply return the value at that point. So how it works, come back to the tree. For example, the very first time I am moving from 4 3 2 1 and 0, and then roll back, and 0 to 2, the path is completely unique, so we need to calculate. Then we jumped from 3 to 2, 2 to 3, and from 3 we move towards 1. So if we are moving from 3 to 1, we already kept that r of 1 contains some value which is technically not equal to minus of infinity. That means that this path has already been evaluated at some time, at some execution, so we don't need to enter into this path. This is a unique path 3 0, so we jumped back and then we moved towards 4 and then jumps to the next branch of 4, that is 2. So when we entered to 2, we can see that the whole 2 number branch is already executed when we were executing 3. So we don't need to enter in the whole branch, and we can leave the value and then jumps back to 4, and from 4 to 1 is already calculated, so we don't need to calculate 1 again. So we can reduce the execution, we can reduce the our solution approach. So we are basically optimizing the technique. So with the help of this memoized algorithm, we can reduce the energy and we can reduce the complexity of the algorithm. After so far this approach is basically a top-down approach, and now we can convert this top-down approach into bottom-up cut rod technique, which is even more simpler. So here we are having r same 0 till n is the new array, because we are moving from bottom to top, so we don't need to initialize r of n equal to minus of infinity or 0. So we simply says r of 0 is equal to 0. So if there is no rod, there will be no price. For j is equal to 1 till n, and q will be equal to minus of infinity. So for all the values of j from 1 till n, first we initialize q with minus infinity, and now we are having another nested loop which starts from 1 till j. So if we move from 1 till n at the time of j, so the next loop will start from 1 to j. It is not going up to the value of n, so we are basically reducing the approach. So we are not passing through those branches which were already resolved. And again, q is as same as we did previously, but here we are not implementing the algorithm recursively. So see this thing particularly, that this approach is your dynamic programming approach. So initially we built up a recursive solution, then we create our solution into a memoized technique. Basically we are optimizing the problem and optimizing the solution, and in this algorithm we are basically converting the recursive solution into an iterative solution. So here we are using two loops to manage all those tracks. We are not calling the function for completing the iteration. So in this way you can see the tree will be in a different manner. These are the following steps which were technically taken by the dynamic programming. First, 4 comes 3, 2, 1 and 0. This is a flat step. The next time 4, 3, 1 and 0 is valid. 4 from 4 to 2, 4 to 1 and 4 to 0 are the valid steps. We don't need to go from 4 to 2 and makes a new path and again and again. So this path which was previously executed or calculated when we were executing from 4, 3 to 1, we don't need to calculate this 2, 1, 0 again when we are calculating from 4 to 2 and 2 to 1 and 0. So the tree becomes reduced, it shrinked. So this approach gives us the idea of converting the problem from a divide and conquer mechanism to dynamic programming solution, and provides us completely optimized structure. This is another extended bottom-up cutthroat technique in which we are keeping the sizes as well. So we need to identify the size at the same time. That what exactly? Previously we were simply getting the cumulative price, the maximum price of different cuts, but we are not keeping the values of those cuts, that which size exactly we need to have the maximum price. So with this, with the help of this algorithm, we can have the value of size as well along with the price. So we can easily implement this technique, and there is no harm in it. So you can see that there is another array S which is keeping the value of j as an index, and it keeps the value of I, which is the size of the rod which we are cutting, and then we can print the value of S as the size. So we can use another small algorithm simply just to print the values of S array. So here we can say that if we are having 4 size initially, if we are getting the rod of 4 length, we will get the maximum price which comes with the help of R as 10 units, and what shall be the number of pieces? We will get the pieces of 2 size each. So for example, if I am getting a rod of 10 unit, so the maximum price I will get from the 10 is 30, and I will get the same size here. So if I'm getting a rod of 10 units, I don't need to cut into pieces, because if I am making pieces, I will not get the maximum price. So I just leave the 10 unit rod as it is to get the maximum price. So this is how we can convert the problem from a normal divide and conquer solution into a dynamic solution, from a top down approach to the bottom up approach, having memoized technique which keeps the value of those branches which were already executed. So thank you.